Okay. So when I was just messing around with this whole ligand and metal idea, that's why some of these compounds have their different colors, because of this LMCT, ligand to metal charge transfer transition. Okay, so it gives rise to some colorful compounds. And here's an example of one, ligand to metal charge transfer. But where we left off was this idea of phosphorescence and fluorescence. And where all did we go here? We talked about lifetime. What was lifetime? Jeffrey, what was lifetime? I was talking about this type of fluorescence, phosphorescence. What's the idea of lifetime?
How long it glows?
Yeah. You could talk about the lifetime of the object, yeah. But when they are talking about lifetime, isn't it up here somewhere, isn't it? Did they mention the word lifetime somewhere?
No, we just talked about it.
Oh, okay, let's add the word lifetime. Has a little symbol tau. So when they're talking about lifetime in these processes, they're not talking about how long the little glow-in-the-dark toy will stay glowing. They're talking about the average time that a molecule will stay in its what state? Excited state, exactly. That's the average time that a molecule will stay in its excited state is lifetime. The average lifetime of fluorescence or phosphorescence is larger.
No, phosphorescence.
Yeah, phosphorescence. Remember, that's the glow-in-the-dark toys. That's the milliseconds and stuff. Okay. Do you know, Mel, I saw a video on what you're doing. It's There's a cool, and I should get the video. I'll get you the video. It's I don't like really anything about biology, so I kind of, when I watch it, but it's a good video. So when you guys are doing the homework problems, I'll Google it and find it. Because I just saw that this morning. In fact, I recorded it and I sent it to myself because I'm planning on putting it in my online course thing. Anyway, so we're talking about phosphorescence. Let's see, fluorescence, like you said, nanoseconds lifetime. It's really fast. Were these the same? What were these black curves supposed to represent, Kevin? Electronic states, yeah. Was this is absorption here an allowed transition, Alyssa, in this fluorescence process?
Yes.
Yeah, and we've only talked really about one selection rule here. What are we talking about, allowed transition? What are we really referring to for electronic transitions?
To jump from the same, like from singlet to singlet.
Spin, exactly. Singlet to singlet, triplet, whatever, right? Delta S should be equal to 0. That's really the only selection rule that we've been referring to. So this would be a singlet state and a singlet state. Okay. Phosphorescence, though, you want that lifetime to increase dramatically. And it does, right? And it does so how? Yes, as an unallowed transition, right? So absorption had to occur. That had to be an allowed transition. So those two are the same electronic state. But then it's what Mel said. What was it called?
Intersystem.
Intersystem crossing. It's two vibrational states of two different electronic states of different multiplicity are just perfectly in alignment, perfect energy, same wave function, very similar, and it transfers from one electronic state to another, right? So all of a sudden it finds itself in a triplet state. But the ground state is still singlet. So it's not an allowed transition. But if you wait long enough, which on the microscopic level is milliseconds or less, around there, and it'll happen. That's how we get phosphorescence. Okay. As intersystem crossing, this is supposed to indicate what? Here's a hint.
It's angular momentum.
Angular momentum. This angular momentum is kind of coupling with what type of angular momentum? Spin angular momentum. Ends up in big J. What was this called? Yeah, J is total angular momentum. But what is this called? Spin orbit coupling. So this is supposed to be how this, that's a very abstract idea in the first place. That's supposed to be how this intersystem crossing is occurring, especially in heavy atoms, I guess. Okay, now on to some new stuff. Mel, if we back up again, we called these what transitions? They start with a V.
Vertical.
Vertical transitions. Okay, Jeffrey. What's going on here then? Doesn't look very vertical to me. What did they do? A Jablonski diagram. This is more my sort of thing because I don't like to draw. I mean, if you want to represent phosphorescence and fluorescence, you can do this. We have to draw these nice anharmonic curves, and you have to draw a different one for every electronic state. And do you remember, anybody, what was the axes for this, for these plots? What were the axes? Potential energy. You're thinking about spectra.
What was it, molecular geometry?
It's molecular geometry. So if you go back to the Frank Condon factor, right? It's a vertical transition, these electronic states, because why? Nuclei didn't have time to move. So there's really way too much information here in this type of plot because the nuclei can't move. Everything's a vertical transition. So why not just fix the molecular geometry? Because that's what it is. It's fixed, right? And that's what this is. The molecular geometry is fixed. So now we can just draw lines from whatever state to whatever state we want. Things aren't vertical. I mean, you're just drawing wherever you want. We're going from this state to that state, so you draw a line. Okay? So that's what they call a Jablonski diagram. Okay? And then on this, but now the y-axis looks like it is what? You recognize that symbol?
Wave number.
Wave number, right? So the wave number of the transition. Kind of nice. It doesn't have to be wave number. It could be energy, right? So one more time, what is selected? What is fixed so you can make a Jablonski diagram? Molecular geometry. Right. Potential energy is fixed. Okay. What's dissociation? Breaking something up. You're gonna, I don't have my little, shoot. Well, you just have to use your imagination. Okay, I pull my little, I have my spring hanging on my weight, pull it down a little bit, didn't dissociate, right? Pull it down a little bit more so the next vibrational ladder, right? Sooner or later, the amplitude's gonna get so big, what's gonna happen? Well, we're not supposed to say break, though. We're supposed to say dissociate. All right, okay. So they're trying to say that, what is this blue thing? talking about? Well, this region of the blue thing is continuum. But that blue plot is supposed to be absorption, right? We've seen this kind of thing. And those, what did we call these little pumps here? Right, this is absorbance, wavelength. We called it a what progression? No, a vibrational progression. You see how each one of these bumps corresponds with a different vibrational energy level, right? So all they did is they put an absorbance spectrum on its side to show you how it's going. And then they're trying to get you to realize, because we've seen these plots before where there's a max, right? There's a V max. After that, it dissociates. The amplitude's too high. Same frequency, just the amplitude. So sooner or later, you go over V max, it dissociates. But look, the absorbance spectrum is still there. It's going down to nothing. So that's our continuum. Take on any energy it wants. There's not, there are no, what gave rise to quantization of energy? Boundary conditions. There's no boundaries anymore. You have stuff broken flying around. So it's, even though they're still microscopic objects, if there aren't any boundary conditions, there's energy can't be quantized. We learned that with particle in a box. So that's the continuum region of our absorbance spectrum.
So that's what is boundary conditions?
In a continuum?
Yeah.
Continuum means you can take any energy you want. So that means no boundary conditions, right? And why are there no boundary conditions? Because there's no what existing anymore above V max. There's no
Vibration?
There's no bond. We just broke it, remember? If we broke the bond, there's no boundary conditions. There's nothing. It's just two atoms flying around if it's diatomic. Right? You take on whatever speed's flying around. There's no boundary conditions. It's totally free. Okay.
And the potential energy is not there anymore. Did you say it's in a continuum?
In a continuum.
You said something about potential energy still being there.
Go back and check the recording. I don't think I did. That doesn't make any sense. Because if there's no bond, there's no potential energy map. I mean, it's gone. There's no boundary conditions. You can't calculate an energy. You know, there's no boundary conditions. There's nothing to quantize. It can't be quantized without boundary conditions. Pre-dissociation. Oh, okay. So this is what you would expect, right? That you get up high enough on that vibrational energy ladder, and then you hit your continuum and your absorbance spectrum, right? And that's what you see here. There's no little blips or no bumps. But in some absorbance spectra, you hit that continuum even earlier, right? You hit that continuum even earlier. You hit it too soon. All they're saying is that in green, I don't know if you can see that, in green is how many electronic states do you see? You see two wells, right? Two black wells? So there's two electronic states. But they try to draw in a third one, and that third one is green. Does the green electronic state have a well? No, it doesn't have a minimum. So that is what do they call it? An unbound state, a dissociative state, right? It's an electronic state that corresponds to dissociated, bond. There's no bond there. It's completely dissociated. So in that dissociated state, the green electronic state, where there's no well, You know, it's just like before. You can get an intersystem crossing kind of idea. But intersystem crossing, really, that term only refers to this idea of going from one state to another state where they're different multiplicity. So we're not supposed to use the word intersystem crossing here. We're just supposed to say, oh, it jumps from one electronic state to a dissociative, another electronic state, but that electronic state doesn't have a well. It's just a dissociative electronic state. So it dissociates. And that's what happens. So you don't get this vibrational progression, even though you should have it. It's kind of weird. It's not all absorbance spectra, I guess, is what we're trying to say. They're going to look like this. Some are going to have a vibrational, lose their vibrational progression a lot earlier. Okay. Internal conversion. We had this word in instrumental, but I don't know if anyone remembers it. Radiationless transition from one electronic state to another. But that's not the complete description, because for all we know, this is a description of intersystem crossing, because that's radiationless, going from one state to another. But intersystem crossing, those two electronic states had different what? Multiplicities. And you can use the word spin too. They're synonymous. So this, if it's a radiationless transition from one electronic state to another, but with the same multiplicity, that's referred to as internal conversion, with the same multiplicity. Okay. Internal conversion. So if you're, go back to the fluorescence picture here. I bet there's a lot of internal conversion in this, right? Because they have the same electronic state, right? It might emit light going down, but it could also be radiationless decay, but they call that internal conversion. Okay. So if you want to see a lot of fluorescence, would you want a lot or a little bit of internal conversion going on?
A lot? Wait, what did you say?
If you want to see a lot of fluorescence, would you want a lot, a high degree or a low degree of internal conversion going on?
A little bit.
A little bit, right? Does that make sense? Because you want everything to be radiative decay, not non-radiative decay. You're just playing around with words, their terminology. Metastable. Okay, now we're getting into laser. What does that stand for again? Jeffrey, what does that stand for again?
Light amplification, stimulated emission.
Resonator.
Ooh, light amplification by stimulated emission resonator. Right. Okay, so we're going to need a resonator. We're going to need an actual physical setup so light can bounce in between, right, and build up this energy. So we haven't described that yet, but we will. So what we're talking about here is the inner workings of this laser, right, the chemistry of it. And what's really needed is a metastable state. So, and it's an excited state. So I guess, how could we describe this? The lifetime is long enough. I guess you could say just long enough. It's just long enough so that this thing may occur. So it just looks like one term leads to the next, but that's kind of how it works. Okay, so if you want a laser, what's kind of weird is you need a population inversion. Well, when they're talking about population, they're talking about population of what? You're trying to build a laser from this material. Population of what? Of the molecules undergoing this transition. And they have populations in the ground state, and they have populations in the excited state. So that's what we're talking about. Whatever molecule or whatever crystalline material, whatever we're talking about, we need a population inversion. So you'd expect the population there to be a greater population where? In the, well, normally though, you'd expect it to be in the ground state, right? 'Cause that's what everything's in the ground state. So you'd expect everything to be in the ground state. So with only that expectation does the word population inversion make sense. Because population inversion means now the population is greater where, Kevin?
Excited.
In the excited state. It's the exact opposite. And you need that. This has to happen for you to make a laser. Okay? So that has to happen. So how does it happen? Well, you need this metastable excited state, the state where a molecule gets into that excited state, it hangs around for a while. Because if it doesn't hang around for a while, you're not going to be able to build that population inversion. Okay? So they call it, if you see this, Mel, how many electronic states do you see here? 3. Good. If you see 3 electronic states, you're reading this right. Okay? So there's 3 electronic states. How many excited states are there, Al? 2. Right, and the good, and the bottom one's a ground state. So I think you're seeing this. Okay, so they call this pump. Now remember, the goal is population inversion. Why would they call this pump, Kevin? What do you think they would? And pumping. Yeah. What are they trying to do? Yeah, they're
trying to force the molecules
into the excited state. Now, how are they probably doing that? How? Yeah. How? If you want to go from one electronic state to another electronic state. Absorption. Absorption of what? Photons. So hang on now. It means you got to have a laser to make a laser? Right? No. But you need light, right? And, well, that's the most traditional way of doing it, is using light. Now, you could also just use electric fields, but you need a transition, right? And you need to pump this population in the ground state to your, right, to an excited state. So you achieve this population inversion, right? So that's what this pumping this pumping is making that. And I've seen lasers where they have these essentially just light bulbs, and very expensive flash lamps would be a better word. Very intense radiation, and they're flashing, that sort of thing. But okay. So here's 2 diagrams. Diagram 1 and diagram 2 on making a laser. Which one do you think would be easier to achieve this population inversion? Laser level system scheme 1 or laser level system scheme 2?
2.
Why 2?
Because there's more excited states. Like it's going from I to A prime.
So, hang on. If you say 2, what 2 states are you getting your population inversion You know, you got to compare two states to get a population inversion. Which two states are you comparing? Going by this diagram 2.
X to A.
X to A. This is A prime. This is A. X to A. You agree?
So is A prime another excited state, or is that
A-
like the ground state?
Good. Good question. The lowest electronic state we can definitely call the ground state. So anything else must be a excited state. So let's take a look at level diagram 1 first. There's less things to worry about. In diagram 1, the population inversion, here's diagram 1. The population inversion is occurring between what two electronic states? Definitely.
X and I.
X and, well, the problem with I, though, is everything ends up going to A. So I wouldn't say X and I would say X and A, right? Because everything ends up jumping over to A. So your population inversion is there's more population in A than there is in X. So that's how you achieve a population inversion in diagram number 1. If you're going to achieve a population inversion in diagram number 2, it needs to be between what two levels? Here's X and A prime. So you want the laser action, this emission has to occur between your two states that you're picking. Is the laser action occurring between X and A prime? Between A and A prime. So you want your laser action. That's what they're saying. They're trying to say that this laser action is between A and A prime. So your population inversion has to be between A and A prime. So the question now becomes, is it easier, can you see it? Is it easier to get a population inversion between A and A prime in diagram 2 or X into A in diagram 1? What would you imagine?
2.
I see 2 also. Can you see 2? Why?
The distance between A prime and A is shorter than the distance between.
Oh, yeah. Oh, well, the distances really don't matter. It's not drawn to scale or anything. And distances would just be different colors of the output of the laser. Population inversion means there has to be more in the excited state than the ground state. So you physically build a laser. You've got this material, and it's all in the ground state. And you've got a gazillion, I don't know how many atoms, right, here. And you have to achieve a population inversion with that? That's bloody hard. That's what diagram 1's saying. Well, why not just make an imaginary ground state, a metastable state? So the only thing, because look at, you're not pumping up to, right now at the very beginning, before this laser even starts, there's nothing in A prime. But that's the lower state. It's super easy to achieve a population inversion with diagram 2 because there's nothing in A prime. Nothing. Yeah, it'll jump to X pretty quick, the ground state, an internal conversion, right? Radiationless decay, but that's fine. We're trying to achieve a population inversion. So having a more complex system like number 2 here will really make that a lot easier. You see that? You don't have to do much pumping at all, and you've already achieved a population inversion. Does that make sense? Jeffrey, did I lose you?
No, I think I got it.
Al, does that make sense?
Okay, so basically you're just saying like the main reason is just because there's nothing in A prime?
That's what I think. That's what goes through my brain. Because at the beginning, at room temperature or whatever, everything is in the ground state. Everything should be down here. And then you shine some light, do something to excite and pump them up to the excited state, I. Well, they don't hang out there very long. They ended up going to A, right? Probably internal conversion. And then, whoa, the chemistry forces a photon to be emitted. But it only goes to here, not to the ground state. And then it slowly ends up over here. Or slowly, fast, I don't know. But the point is the population inversion between an excited state and a lower state is right here. So it didn't have to, population inversion, I guess the trick to it is it needs to be a population inversion between an excited state and a lower state. It doesn't have to be the ground state. If it's the ground state, it's going to be super tough to achieve a population inversion. You have to pump a lot, pretty much the entire material, into the excited state. Over half of it anyway. Okay, so the output of a laser is called coherent radiation. Now, why was that again? It was on our last exam. And it's the SE part in laser. Stimulated emission. That's why it's coherent. What does coherent mean? Right. I have a, let's say if we could somehow zoom up, into our laser cavity, right? And we're getting purple light or something, right? So there's a purple photon in there. And another purple photon's emitted. Coherent means it needs to be in, if I'm going to draw another one, with waves instead of dots, they have to be in sync. So another one. So the amplitude just keeps building up. But that was the idea of that was stimulated emission, right? Because you have this excited molecule, and this photon comes by. The photon that exactly matches the light that molecule wants to emit. It exactly matches that energy. So then it stimulates that molecule to emit. And when it stimulates it, man, it's just the exact same. It emits a photon, yeah, but now you got two photons, and they're exactly in sync. Stimulated emission. So what we're missing now is the R, and the R in laser is resonator. Okay, so we need to have some mirrors or something here. And what they have is the in mirrors are just partial. And this one is going to be 100%. So have a mirror that's, you know, it's not going to reflect 100% of the light. It'll let out, you know, 5%, 10%, 1%, 0.01%, whatever percent you want out to help you build that laser. Okay, would be the other end. I think they're usually curved too, because it'd be a lot easier to build a laser with curved than flat. But okay, so what they're trying to say, here's your material, right? Your diode or whatever your lasing medium is, and this pump, pretty much it could just be surrounded by, I can't draw, how do you draw a flashlight? Surrounded by lights, right? It could be surrounded by some really bright flashing lights or something, but that's the idea. And then this doesn't look like much, but what you can do is you can, inside this laser cavity, you can put a little crystal, stick it in there, and have it hook up a little piezoelectric to it and have it oscillate, right? And we have those things all the time. And for example, in our that sonicator, right, to clean stuff, right? There's a little crystal in there, piezoelectric, and just oscillates. Well, put the same thing inside a laser cavity, and then your output isn't a laser pointer anymore. Your output is light, laser, no laser, laser, no laser, laser, no laser. So all that crystal, vibrating crystal is doing is it's messing up the alignment. And you kind of have an idea of what alignment is in a laser by messing with that Michelson interferometer. When it was out of alignment, you lost your fringes. Okay? So what this crystal is doing is it's just messing up the resonance or aligning it, with its oscillating. And the reason why this is they call it mode locking. The reason why this is such a useful thing is here's a big one. If we could figure out, energy is an issue, right? I personally think the only way out of our whole energy issue is solar. And if solar is the only issue, you could be messing with solar cells and all that kind of stuff, but come on. Why don't we the answer is photosynthesis. Nature's already got the answer. We just got to figure out how it does it. And then, man, we're set. So one thing that they're working on is they're using a tool like this to figure out what photosynthesis is. Now, what does that matter? Well, in photosynthesis or metabolism, what goes on inside a cell, whatever, you can apply this to a lot of different things. There's a lot of different processes going on, not at the same time, but one after the other, and very often on very fast time scales. What's going on inside a DNA drug interaction complex? Well, what you can do is work with the laser frequency that this drug complex actually absorbs this light, and you've got light, no light, and light, no light. You can get time-resolved spectroscopy. You can see an actual, with a lot of experimentation, you can see and make a chemical movie as to what's happening in this chemical system over time, and really see the inner workings of one step to the other step to the other step. And you build chemical models to try to model your data in the lab that's time resolved. And if you have the wrong model, it won't match. So it's really, really useful. We were messing with that for a while. Okay. Here's a pictorial summary of laser action. Right? Here's room temp. This is what you would expect. Everything in the ground state. Maybe you got something popping up in the excited state, right? Not a whole lot. But you do the pumping action by whatever means necessary, right? You get more in the excited state than in the ground state. Or probably not even ground state, just another state, right? You use a 4-level laser, it's even easier. And then out goes your laser action, right? Once one emits, it just stimulates the emission from the rest. You need your resonator, you need your mirrors in there, and you're good to go. So see if you remember this. If you wanted to make here's a red laser pointer. Why was it that about 7 years ago, I think, I would say, you couldn't even buy a purple laser pointer?
Harder to make.
Why is it harder to make? It's shorter wavelength, yes.
So the scattering?
Einstein coefficient of emission. That's this random one, right? Not stimulated, just emission, and that magnifies itself. It's much, much worse for shorter wavelengths. Okay, so that wouldn't help this at all, right? You get that emission to happen without stimulated. You'd be fighting it. Okay, so here's some homework. Calculate the percent reduction in intensity. What the heck? Where's this stuff coming from?
Yeah, that's not the homework we had.
It's not the homework you guys have?
Probably 12.5 census.
Really? Twelve. 12, 25, 26. Oh, I have it crossed out. So cross out 12, 25, 26, and 27. And just write 1, 2, 3, 5, 6, 7. Yeah, that's right. You guys have the defective stuff.
Should be updated.
You would think. Looks like we're never going to do 12, 25, 26, 27. Because the next one, you cross those out. Yeah, that one's 4, 8, 9, 10. Do you have 4, 8, 9, 10?
No, 12, 25, 26.
Yeah, 4, 8, 9, 10 is the next one. All right, let's get you started on these. We have a couple equations. Yeah, probably have to remember your instrumental, or you have to look in the book. I think we talked about this stuff. A equals EBC. You remember this stuff? What are these things? What's A? Absorbance. My little epsilon.
Coefficient.
Yeah, that molar absorption coefficient. Little b? Path length. We should probably draw a little cuvette or something here. How do you draw a cuvette? Oh, I can't draw a cuvette. But draw a cuvette, right? And then this length of the cuvette is what symbol? B. Okay. And then I have something striking it. And then if it gets attenuated, it'll be a little bit less. What's less? The symbols are up there. The eyes. Now, where do I put the eyes? On my little diagram.
Should be the left arrow, should be IO.
IO and I. The O means incident. Yep. Okay. T stands for transmittance. And no one ever does this, but I wish they would. It would make a lot more sense to put little subscripts on these things. Does it make sense to put a little subscript on the B?
No.
What's my little subscript? Can you read it?
The lambda?
The lambda, which stands for wavelength. So how about the C, Jeffrey? That's probably what?
Concentration.
Concentration. Yeah, so it wouldn't make sense to put a subscript on that one either. But absorbance it does, transmittance it does. Okay. So all those are wavelength dependent, just not B and C. Okay, so they are after calculate the percent reduction in intensity. So pretty much, what are they after? If you can't figure this out, it's pretty hard to find. It's a start even. Percent is percent, but
Percent difference.
That's the I over I.
yeah. So if I over I naught is 25%, I think what they really want is 1 minus I over I naught, right? Because if you get 25% through, if T is 25%, that means 25% got through. But what's the percent reduction? That would be 75%, right? If 25% got through, 75% would be the percent reduction. So I think if they want percent reduction, it's really 1 minus this. That's how I see it. Oh, times 100, right? To get percent. Does that make sense? Jeffrey, did I lose you?
No. Makes sense.
Okay, so how are you going to solve for this?
Let's solve for A.
Yeah, solve for A.
And then A is 10 to the power of
And I think the only part that's kind of confusing is you got to watch your what? Your units. Look at it. They have centimeters and they have millimeters in here, millimoles, and then you have moles. At least they stuck with liters instead of putting a milliliters in there somewhere. So make sure you make all the units consistent and you'll be fine. I would just go to moles and centimeters, I guess. But are you ever going to use this 270 nanometers?
No.
Nope. Oh, you guys got to do your homework while I go look at my video, find my video. Well, one quick video. Won't take very long.